So let me tell you a story why I started to care about state machines and try to fix some misconceptions about them. And that's where we'll start here today. So back a few years, I was an intern in a company. It was a Christmas period time. I was ready to go back home, and I noticed that a lot of developers were, really hard working. And I asked them, it's a Christmas period. Why do you work so hard right now? And they replied that they have a, contract going with a country which doesn't have, holidays in the Christmas. So they had to be on call, and they had to dig into the possible problems which they may encounter. So, I came back from Christmas. I was an intern. I was working, right? So when I got back, I asked them, how did it go? And they said, well, Kris, we had a lot of issues. And, specifically one, which, it took us all the Christmas to sort out. So they didn't go back home. They were really annoyed. And, it was bad. And the problem was that, let me explain the system they were working on. The system was really simple. It was just having some inputs, manipulate them and had some outputs. So not the rocket science. But the problem was that they haven't had proper practices, and they found that they didn't reset the Boolean variable in some switch, in some loop, in some for. And that was introduced by the bad merge request and the conflict. So, I learned quite a few things out of that. The first one, well, I didn't work for that company. They worked during the Christmas time. The second one, I learned that, well, they didn't have a good practices because they didn't test it. The way they found the bug, it was by reviewing the code. So they didn't have any good practices. So again, I didn't want to work for that company. But the main problem I learned is that they didn't have the declarative way of expressing the application flow. And therefore, they had to compare different solutions using the code review, the diff between the working and staging, instead of being able to figure out upfront what was going on. So I asked them, why you didn't use the state machines, for example? Well, they said there are performance issues and other issues which we didn't want to deal with. So this talk is about how we can actually clarify those misconceptions and hopefully spread the word about the state machines. So let's dig in. But at first, let's introduce a problem. So if you have a healthy company, not the one I was working on, we'll get the requirements from our product owner or whoever is our client. Let's do that in TDD, BDD style. So we have a feature connection. We have a scenario, established connection, very simple TCP approach. So given I don't have a connection, when I receive a request to connect, then I should try to establish the connection. When I got an acknowledgement, I should be connected. Very simple and easy way of defining the requirements. We have obviously more the requirements than that. How can we actually implement that guy? Well, let's take a look into state machines. Obviously, there are different ways of doing that, but we don't consider them in that talk. We'll talk about the unified modeling language. Is everyone familiar with that guy? Yeah, more or less everyone. So it's a standard. It's specified in img.org. You can read it. I think it's even worse than the C++ standard to read, so I don't advise you to do that, but you can. There are a lot of features specified in it, so that's useful. So our features, as scenarios, we can actually translate into the state machine. And how does it look like? So I guess everyone has seen some pictures like that. We have an initial state, disconnected. We have an event connect, and we call the established action, and we transit to the connecting state. And if we are, for example, in connected, we have the ping event. If the guard, which is in the square bracket, is valid, we call the reset timeout, and we stay in that state. Otherwise, we don't call the reset timeout, and we don't do the transition. Make sense? Easy to follow. Everyone knows that. So today, we'll try to implement that guy many different ways. So we'll take a look into naive solutions. By naive, I mean C++98 features, if-else, switch enum, inheritance, state pattern. We'll take a look into STL, and std variant might be used to implement state machines. Coroutines might be used to implement state machines. And we'll also take a look into the boost libraries. Oops. Sorry about that. Let's first introduce some common implementation, common across all the solutions so that we don't have to repeat ourselves all the time. So the event will be just simple structs. We can start from that, although they may have data as well, but we don't really care about it in our case. We have a guard. One guard is valid. It returns true by default. It takes an event. Nothing special about it. We have an action, which will just print to the output. We'll use put just in order to see in the godbolt whether it's inlined or not. Otherwise, we would have a lot of code from stdc out or IO streams, which we don't really care about. Sorry about that. So let's take a look into naive solutions. So the first one will be the if-else. We'll start from implementing the connection class. We'll have, obviously, 3 booleans to represent our states. The state will be implicit because they will be implemented in the code. By default, the disconnected state is true. Other ones are false. And when we process event, which is the connect event, we verify whether we are in disconnected state. If we are, we call establish, which is the action. And after that, we have to reset all the states, because that's what you learn from the story in the beginning, that you always have to reset all the states, just in case. Because if you have really nested version, you may actually forget about it. And the transition is just setting the connecting state to true. What about processing the ping? We get the connected. We verify whether we're in the connected state. We check whether the guard is valid, and we reset the timeout, and we stay in the current state. Makes sense, right? So what about the godbolt? As you notice on the left side, on the bottom, there are 64 lines of code. Not bad, not a lot of boilerplate, and everything is very well inlined and optimized with flags we can see on the top. So that's good. And why is that optimized? Well, it's an if and else. It's really easy for compilers to see it through. So that's a great thing about the if else, right? So it's inlined in GCC and in Clang. I just shown Clang, but GCC produced the same output. There's no heap usage. That's great. We don't have to care about shared pointers, unique pointers, or anything like that. There's a smallish memory footprint. However, it's not ideal because we have 3 booleans. As a state machine, we can only be in one state at a given time. So that's a waste. It's hard to reuse. And to illustrate that, let's see. It's so hard to reuse that I guess everyone has seen the code when you have multiple ifs, switches, and everything is nested. It's like, how much can you go? I don't know. It depends on your, I guess it depends how many spaces you use for your tabs. I don't know. It can go quite far. But yeah, obviously it's hard to reuse because it's hard to implement those guys and maintain. So that's not the best solution. Let's take a look into a different one, which is still very easy, and everyone probably have seen it. Switch and enum. Everyone's love it, I guess, because it's so popular. You can see it in any legacy code base. So it's good for the state machines from the perspective that only one state might be active at a given time. So we use enum. So it's pretty much the same as the previous solutions. Instead of Boolean variables, we use the enum state with the three disconnected, connected, and connected states. Disconnected is the default one. When we process the event, instead of if, we do the switch to handle current state. By default, we break. And if you don't know, default is just a label, so it might be put anywhere in the switch. In case of disconnected, we call establish. We change the state. We break. Nothing really spectacular here. And the same case for the ping. If we are in connected, we verify whether the event is valid. We reset the timeout, and we break. So far, so good. What about the performance of that guy? Again, compilers are really good in optimizing simple things. And switch is one of the main constructions in C++ in which compilers are really good at. So we have 65 lines of code, pretty similar to if-else. And everything is optimized very well. So that's great. But what about the switch? What's bad about it? Well, it's inlined. That's good. We fixed the issue of the memory footprint. It's 1 byte. That's fantastic. There's no heap usage again. It's still hard to reuse. We still have, a lot of nested switches and ifs and fors and everything like that. It'll be hard to add a new state and maintain that. So in a sense, it's like, you code for 6 minutes and debug for 6 hours. Even with the good test coverage, it might be difficult to find those bugs. So yeah, maybe that's not the best solution either. Let's try a different one. We all know that object-oriented design is great, right? We can use shared pointers everywhere, throw them away. So yeah, let's do it. Because we care about the performance, so yeah, we'll see. So we have our state, which is an interface with a lot of process events for all the events we can handle. And after that, we implement it per state, on per state basis. That's the thing which actually gives us a lot of goodness, because we can implement a state transition. We can add a state and transitions to it without changing the connection itself. So that's valuable. It means that a lot of teams can work on different transitions and combine them together. So that's positive. So how do we do that? We have a disconnected state. We inherit from the state. We have the constructor. Well, we have the connection which we have to pass through. And in case of connect, notice that I use final here, because that will be important for the devirtualizations, possible devirtualization. And we change the state to connecting. It's pretty much the same implementation as we've seen before, just a bit different way. The same about the ping. We have to implement here the ping and probably also other events to satisfy our requirements from the UML state machine, which we described before. But all in all, it's very simple. Sorry, it's playing with me. What about the performance? Well, we have a bit more lines of code because, well, it's object-oriented design. We write a lot of code, boilerplate code, just to satisfy the design. And unfortunately, we have the vtable. It wasn't devirtualized, although we had final. We have, for Clang and GCC, we have around 220 lines. Not ideal, not perfect. And I'm using the newest Clang and the newest GCC here. And all the examples are on the Godboard. You can check them out yourself and experiment if you want. So what's good about the state pattern? As I said, it's easy to reuse and extend because we can add the states quite easily by just adding a state, inherit from the interface, and just add your transitions you want. That's cool. It's object-oriented. That's what we want from it. There's highest memory footprint because we have to allocate everything on the heap, which we have to use. And we have dynamic allocations all over the place, probably shared pointers, unique pointers, all the goodness. But because of that, it's not inlined. It's not even devirtualized in our case. So that's bad, because we care about the performance. So although this guy is pretty good from the developer perspective, it's not really good from the production perspective because it doesn't give us what we really need. So so we scanned through the naive solution quite quickly. Nothing really new about it. Let's take a look into something else. It's like if I could pick one thing which C++ is really good for, I'd say is the writing libraries. And one of the best libraries available is STL. I hope you agree with that. And since C++ 17 and C++ 20, we have at least 2 new ways of implementing state machines. One of them is std variant. Everyone is using std variant. Who likes it? Yeah, it seems like half-half of the crowd. I think it's a very powerful idea. Maybe we'll see how powerful it might be used for the state machines. So here, let's take a look into connection. We got back to the one connection class instead of having it per state. And right now, the states are implemented using the types and structs, which is very powerful for us because they can have data which we couldn't have before when we used enum, for example, or a Boolean variable. So keep in mind that although we won't have an example here, we can have the data for the states which may have a different stuff in it. So disconnected may not have anything, but when we connect it, we can have an IP, specific IP, which will be just active and available for us to use when we are in that state. Because variant might be only in one given state as well. So that might be very handy for us. And we declared the variant as the state with the disconnected by default. How do we actually handle the transitions? Well, we have to do the visit on it. Overload is just an idea, and it's proposed for C++ 20 to choose which lambda to call. So we don't have to implement a lot of boilerplate to satisfy that. We could use the generic one and use if const x, for example, if you want. But overload seems to be cleaner in that case. So if we get the disconnected, it means that we in the disconnected state, and we got the connect event, we do the same. I guess all of you can see the similarity to previous solutions. So we call establish, and we change the state to connecting. The next case is just to satisfy the compiler, because it's generated compile time, so we have to call it for all the events, all the states possible. So in case of connecting and connected, we just discard those guys, because we don't care about them in that transition. Make sense? So what about the ping? In the ping, we have actually a very similar, but even an easier way of doing it. We can just verify whether we're in connected state using getIf, which is the part of the interface of std variant, verify whether the guard is valid and satisfied, and there is a timeout being called afterwards. We stayed in the same state, so there's no issue here. What about the performance? From the Godbold and the newest and greatest stdlib and Clang 7, we actually get it being inlined. So that's fantastic. It's not as good for GCC. GCC doesn't inline it at all. It's 140 lines of generated assembly with mysterious vtable being there. We have 70 lines of code to implement that. So all of the implementation is very similar to the previous solutions. As you could probably see, it's very similar to switch and enum. Instead of enums, we just use types, which gives us RII and a lot of benefits. So if you sum up the variant, it's quite small memory footprint because we use the struct. The struct is 1 byte. So if we store the variant, we store the max size of all the states, which by default would be, let's say, 1 byte in our case because we just have the empty struct. Plus, we have to store something to know, which one is actually active. So that depends on the compiler implementation. That might be 1 byte, 8 bytes, whatever. But the footprint will be quite small. And it will be really efficient because we can use those structs to add the data to it. So for example, we can have an ID or last ping or whatever we need for those guys. So that's handy. Also, variant integrates very well with the expected and static exceptions, ideas, because we can actually return an error, which is just part of the variant or expected type with some error case, which we couldn't do before. I won't be talking here. It's like we have exceptions disabled in our cases just for the performance reasons. But error handling is quite important, and handling the errors in enum or switch, it's not ideal. We probably would end up throwing exceptions or something like that, or using the return codes or global variables or something like that. With variant, we actually don't have to do that. We can return something unexpected, which is nice, which is good. It's inlined on Clang. That's good. It's not inlined on GCC. I guess that's bad. But yeah, there's still a room for improvement, and it's quite a decent solution for the simple state machines. It doesn't offer a lot of capabilities besides simple transitions, but it's still very useful. And having the efficient memory footprint is quite neat. It's quite hard to reuse, though, because it's very similar to the switch and enum approach. So we have to, if you have nested state machines like hierarchical state machines or composite state machine, we'll have to have a visit inside the visit inside the visit. You see the pattern. It's not much better than if else, if else, if else, right? OK. So let's get to the good part and the newest part we can actually use in C++20. So coroutines. Coroutines are a new way of implementing state machines as well in C++20. Has anyone experienced the coroutines so far? Tried them out? Yeah, quite a few hands, not a lot of hands actually. So yeah, coroutines, we'll try to dig a bit more into them in a sec. So notice that in our case, the connection won't be a struct anymore. It's not a type. It's a function. So that's the first difference between coroutines when using coroutines as a state machine. Because because coroutines are functions, they're called resumable functions, and we can use them to basically as a functions. So notice on the line, the second line, we have the for, infinite for loop. That's odd, right? Why we would have infinite for loop? Well, we need that guy because we can actually use the coroutines to resume and suspend. And that's where the co-await is for. And if we don't get an event which we want to come back, do the loop, and suspend again in the co-await. It's a different way of thinking, but you can think of it like the state is the position in the functions when we in the function code in a sense where we at. So here on the third line, we have the co-await. We wait on the event. If we get it and the event is the connect, we do establish, and we go further, which means that we will be further in the function. If we don't get event which we satisfied, we do the loop, and co-await will suspend again and wait for it to be resumed by a process event call. Notice that I'm using here a single-threaded application. These coroutines are often associated with asynchronous ideas, but you can use them in the synchronous way very efficiently as well. So there's nothing about being here like multi-threaded environment or something like that. It could be the case, but it's not in our case. So that's very important. So you can use coroutines in a single-threaded way. So right now, we do a second loop because we want to be a bit further in the function. We never come back to the first loop again, in our case, for example, because we transit a bit further. And right now, we stay here, because when we are resumed from the co-await, which is on the second line, on the second part. We won't be resumed before that guy. So I hope, I'm trying to make it clear, but it's really hard to think of it if you don't know what the coroutines are. We are going to be resumed from the co-await call in that place. We won't be resumed anywhere else. So we do the loop because we have to verify whether we are established, whether we got an established event or not. I hope that makes sense. There's a question?
Yeah, what's the end label for?
The question is, what is the end label for? And that will actually figure out in a sec, because we need it for that guy. So as you see, we have a lot of for loops. And the best way to get out of the nested for loops is to use go to, right? So I hope that's answering your question. That to get to the end, it's a different way of thinking, but you have to think of it as like we have these functions. We are in the position. At some point in that function, we are resumed from the point the co-await was being called, and after that, we react on the event. And all this hassle with the continue break and go to is just to go to the different for loop part of the function, because we always stayed in that function. So yeah, it is possible with the coroutines. That specific implementation is quite difficult. But as was mentioned, we use goto. So maybe states are really implicit here, by the way. As you notice, I pointed them with arrows, because we don't really need to know the state, because the state is represented by where we are at the function. Which is like, intriguing, right? It's not really what we actually think of states. But maybe we would like to take a look into that a bit further. So what about the performance? We have more code. It's more boilerplate code to implement by default, because we don't have all these facilities. Coroutines are implemented in the core language, but we have quite a bit of hassle to satisfy the interfaces. You can check it on Godbolt and should try it out. The interface is quite difficult to deal with. And therefore, there are different proposals how to deal with it. However, it wasn't optimized very well. Although coroutines can be optimized, especially yield might be optimized very well, and the generators, the co-await seems not to. And we pay for the heap allocations. Not great. So to sum up the coroutines, what is good about it? The structured code is actually really, really neat, right? We can use ifs, else, fors, maybe for loop, not especially in the way we would like to, but we can still use them. So for everyone who is new to the language doesn't have to learn libraries or anything like that. They may just use the language and just have to understand the call way it will resume you at the point you were suspended. Pretty cool. As I pointed out, you can use it in a synchronous environment, but you can also use it in an asynchronous environment very easily, which is not really a case with any other solution which I will be presented here. There's a learning curve to it, definitely. It's a different way of thinking, so yeah, you have to get used to it. Might be worth it. Requires a heap. That might be not the case in the future. I don't know. I just checked out the Clang implementation because GCC doesn't support coroutines. I'm sorry I didn't bother with Visual Studio, but I wouldn't expect it to be faster than Clang implementation. Even Gore said that the MSVC implementation was experimental and Clang is doing it right. So it wasn't elided. Unfortunate. We have these implicit states, which is good and bad. It depends how you look at it. As depending on where we are in the function, we know whether we are in the given state or not. That's good or bad. I don't know. It depends. And the call weight returns a type. So it has to be a common type, sort of, right? Because we cannot return different types unless we use variant or something like that. So that's not ideal either. And I have to admit, these for loops are quite weird. OK, so let's just do the goto just for the fun of it. Because we can. So it's pretty much the same example. Instead of having the for loops, we need the first for loop because the state machine has to go forever. But besides that, we don't actually need them. Instead, we can have labels if we really want. Disconnected label means disconnected state. Connecting label is a connecting state. Yeah. And basically, after that, we go to the connected state, which is everything is just described by the label. And after that, we can do goto, which seems actually quite even more neat than, that's the way we, exit the loops if you have really nested ones and we don't want to do the checking of the booleans. Well, that's a good solution. I don't know. But it's definitely a valuable solution with coroutines. It seems like a function, changing the position in the function might be used with the goto. Please don't quote me on that. I'm not saying the goto is the solution here. I'm just saying there's an option. You can explore it yourself. And yeah. So if it comes to performance, still the same amount of code, basically. We still have allocations, didn't help with that. We didn't expect goto to help with allocations, though. I hope. So what about the summary? We don't have these infinite loops anymore. Pretty cool. We didn't like them. We have explicit states, which we can treat as a positive or negative, depends whether we liked it before or not. And we have the goto. And the story about the goto, you never know where you end up. Therefore, maybe goto is not the best idea. One more different variant we can use coroutines with functions and variant. So if you think about the disconnected state as a function, we can actually come back to our for infinite loops. Sorry about that. And just have the state being represented as a function, separate functions, and use the coreturn to go to the different state, which is quite handy because we can separate the functions. It's pretty much the same for any other event, state transition we want. So you have a connected state, which uses the for loop for the same reasons as before. And we just, there's a question?
So where is in? You have in as a global variable?
Right, so the question is where is the in? So those guys are part of the connected class which has an in. Sorry about that. So yeah, we actually in a bit higher scope, we could possibly pass the in into our functions, but yeah, it's basically we have a connection class which has an in as a variable, and we can use those guys like that. So yeah, that's very neat. Performance didn't help, actually made it worse because the variant. We used the variant to have the different types of the return of co-weight because we couldn't deal with the common type, so we wanted to have something more flexible, but yeah, it didn't help. So with the functions, we can use them quite easily. We can add in new state behavior. We have type safe events. And it's fancy. It's a bit like Apple new headphones. They can easily get lost. And you can easily get lost with coroutines, I guess. So what about the boost? So we talked about the libraries. STL is great. Boost is maybe even better sometimes. Sometimes it's not. So let's compare a few other solutions. We'll take a look into state chart, MSM, which are available in Boost. You can download them, use them right now. And SML. SML is the library I'm the author of. And we'll just take a look. It's not a Boost library. It's just called Boost to confuse everyone. No, the reason is it's aimed to be a Boost library. OK, sorry about that. So let's take a look into state chart. Has anyone used state chart? Not a lot of you guys. So let's take a look how we can actually implement a state machine using state chart. So we have to change our events to inherit from the state chart event, which is a CRTP thing. Well, not the best start. We have to do some more boilerplate code. But you can deal with that. Actions. Unfortunately, state chart is more like the state pattern. It's object-oriented kind of design. So we have to inherit from the state machine. The first argument parameter here is the CRTP thing, and the other one is the initial state. So you have to have a bit of knowledge how to use that guy. And all the actions have to be put into the connection implementations just in order to be usable by the state chart. So as in the state pattern, we implement that using the per state basis. So we have a simple state, which we have to inherit from. We pass the type we have, the connection we use, and we have the reactions. And the reactions are basically the list of transitions. So you have to be able to read it. So it's a transition from the disconnected state on a connect event to the connecting state. Connection is the class, and we have the established event. So it's basically like before with switch and other cases, it's just less robust, less easy to follow, I'd say. We can also have a custom reaction. So on the bottom, on the connected, we have the ping, which is a custom reaction, which allows us to do the guarding and calling the, it allows us to do anything we want with the state chart and the transitions. And we have to discard this event because we don't transit. Otherwise, we would just call the transit on it. Performance. 60 lines of code and 2,000, almost 3,000 lines of generated code. Well, not great. So to sum up, it has a lot of features, though, UML related, which we don't even cover here. So that's good. It's the learning curve. That's not great. It has the dynamic allocations, dispatch, high memory footprint. So they introduced MSM into Boost, which is much faster. However, it's really based on macros. There's a different front ends for MSM, which is, I'm using this one because I find it the best to be more expressive, and that's what I really care about, the expressiveness and the performance. So you have the events which you have to define with using macro. There's another macro to define the states. There's another macro to define actions. We have to pass all these parameters around. For guards, guard is an action, just returns boolean variable. It's quite a lot of boilerplate. But we do that, all of that boilerplate is just for this guy. And this guy is awesome. It's a transition table in which we can actually read and reason about the flow of our program. So if you compare all the solutions, this one, in my opinion, is much better. You can easily read it. You read it the way that you say, I'm in this connected state. When I get a connect event, I call establish, and I'm going to connect in. That's really powerful to reason about and look at. So all those macros are worth it just in order to have that guy, in my opinion, because it gives us, really easy way to reason about the application flow. Obviously, we have more macros and one not a macro thing. What about the performance of that, guys? Well, it's not a lot of code, 80 line. And the performance, you can see that there's quite a bit of assembly generated, but it's not a bad assembly. It's not always about the size if it comes to assembly. Because here we have a just jump table generated compile time, so all the transitions are just jumps, which is not bad if it comes to performance, and we'll take a look into that as well. So just keep in mind that having a longer assembly is not always bad, unless it's inline, then we want the inline version. The summary, so it's declarative and expressive. As you notice, I hope, in the state machine transitions table, I love it. I think that's the way to go. There's this part, which is O1. It's jump table generated compile time. It has UML features, small memory footprint. There's a learning curve. It's DSL-based. Not everyone likes DSLs. It's macro-based. That's terrible. We don't want that. It compiles very slowly, so if you run it on Godbolt, you'll get a timeout. So in order to get the results of Godbolt, I had to run it locally. But you can still click it. I don't know, maybe Matt will extend the time. I don't know. It's really slow to compile. And the error messages, well, you don't want to look at them. It's MPL 98. So yeah. So that's the reason, that was the main reason why I actually implemented a slightly different version of MSM using modern C++ features. At first, I started with extended MSM, but that was just quite painful because it's C++ 98. And in SML, we can do that. I think that's even more powerful than the MSM because, well, we don't have macros. Yes, we don't have gotos. That's even better. Everything is easy to follow. It's C++ 14. We have the transition table, really easy to read and follow. Everyone agrees? Do you find that easy to follow? Easier to follow than if-else nested switch? Yeah, I see the thumbs up. I like it. So yeah, that's great. But you know, we don't want it just for the sake of being able to write expressive way of code in C++, because C++ is all about don't pay for what you don't use, right? We care about the performance. We want to have the best performance possible. We want to be able to pick how we want to optimize that guy. But the interface is pretty neat. So let's stick with the interface, and let's give us the capability to switch how to change the strategy, how we actually dispatch events. So SML has different policies at compile time. So we don't pay at runtime for anything in SML. But at compile time, we can choose which version of the dispatching strategy we want. We can have a jump table that will be generated compile time jump table like with MSM. We can have a nested switch. We'll take a look into those guys. If else, fault expressions. We don't have coroutines yet, so we can't use coroutines as a backend, but that's an option as well if you really want. So I think that's really actually neat idea to be able to switch the backend policy and have really nice common interface, because if it comes to performance, you always have to measure, right? So it's not always that the jump table will be the best. And from my experience, it's not always the best. So let's take a look into the dispatching policies. If else. So assuming that we have some mappings and states, and we have just a dispatch call which takes the current state and the event. So that'll be the backend interface for dispatching the policy. What we can do with that? Well, we can actually call it recursively for as long as we find whether we are in the current state. If we are in the current state, we will call the execute, which is just the transition. If we're not, we'll call ourselves again with next iterations and the next states, so that we'll be able to call it at the end, possibly. If we run out of states, well, we don't call any transition, and probably it's just unexpected. And that will be very well optimized in GCC and Clang. It gives us exactly the same code in the assembly as before. So that's fantastic. Switch. We have the same case, and we do yet another trick with the switch, nested switch. So in default, we call a dispatch again, which we'll call with the next ID, which we'll call the switch again. So we have this nested switch, which is generated at compile time for us. And if you have the case in which we care about, we call the execute. So is that optimized? Well, yes, it is. So it's optimized in Clang and GCC, and it gives us the same result as the switch did. Notice that on the left side, I highlighted how to switch the policy. By default, we don't have to pass it through, and the policy will be the best one, which is for the compiler, in a way that compiler could actually optimize that guy. What about jump table? Jump table is not that straightforward, but it's not difficult either. We have the states. We have the dispatch table kind of type for the function pointers. And we just generate an array for all the events. And after that, we just jump according to the current state with the event. So that will give us more code, less than MSM actually, but it won't be fully optimized, neither in Clang nor in GCC. But from the performance perspective, sometimes it's much better than the inline versions. It depends. Yeah, we have to measure those guys. And yet another solution is the fold expressions, which is like addition for C++ 17. And what we can do here, we can just fold through all the available events with the available IDs, and we just execute when it matches. It's pretty much the same as recursive version, just not recursive. So that's pretty handy. And fold expressions are actually very well optimized as well. So it gives us the same output as if-else or as switch enum. So yeah, that's handy. Nice to have. So the summary, the main benefit of using libraries like SML is being able to build in expressive. We have these UML transitions being visible quite well for us. The declarative flow, being declarative is always better than not. We can customize it at compile time. Awesome, that's what all C++ is about, right? Customize it at compile time. It's inline. This part is a 1, fantastic. Has fast compilation times. We'll see that in the results, in the benchmarks, in the sec. It has additional features which we don't talk about, but it's obviously a library, so it's much more powerful than just the transition. We can't compare that to the variant, which is just a way of using it for the transitions, but it doesn't have anything else. There's a minimal memory footprint, so the size of connection is just 1 byte. There's a learning curve. Obviously, it's a library. And it's DSL-based, which is a good and bad. Depends on how you look at it. So if you sum up the solutions, we can quickly get through them as depending on how the state is represented, how the transition table is represented, and how the transition is represented. So state might be represented by Boolean variable in if-else, enum, maybe a class, maybe an union, maybe a function, or maybe even a type only, like in SML. And transition table might be per state, which means that object-oriented design using it per state. Or you can have it global, where you see it, all of them. And the transition is implicit or kind of explicit. Implicit means that you have to look through it somewhere in the code to find where you actually do the change state. And explicit, which is usually better than implicit, means that we can actually take a look into one simple, source code, one file, a few lines of code, and we see everything just happening. There's no surprises afterwards. OK, so sorry. Let's take a look into benchmarks then. How does it compare? Yeah, I was talking about for almost 50 minutes about those solutions. We compared the Godbolt results, but we have to measure to be sure which one is the best if it comes to the measurements we're going to take. So in order to do that, we changed our actions and guards to have to verify, to access some memory so that it won't be totally inlined. And the idea is that we randomize the events, and we run the process event on those guys with GCC and Clang. The results will be for Clang, but with GCC it's the same, basically, besides the variant. And we have to use Clang because we have coroutines in Clang. We don't have them anywhere else for now. So lines of code. The less, the better. SML is really good here because it's optimized for being expressive. Design pattern, state pattern is not the best one. We have to write a lot of code. As usual, with the object-oriented design, there's a lot of boilerplate. MSM, although it's really expressive, it has a lot of boilerplate code to write with those macros. But besides that, it's quite even. Assembly lines, so that's what we compared before in the Godbolt. We see that there's naive switch and if-else and SML, since it's using switch or if underneath in those cases, are very well optimized and inlined. State chart, if you care about performance, don't use that guy. It's not the best one. Coroutines and variant, Yeah, they not terrible. Not ideal either. It depends obviously on your case. In your case, on your case. If you care about the performance, probably you want to use them. But if you're not that bothered, then you can. So that's the main kind of benchmark, which shows the runtime performance. As I said, having longer assembly doesn't mean that it will be faster or slower. So you can see MSM had really long assembly lines because it generated jump table at compile time. But actually, it's quite fast. Variant is quite fast as well on Clang, not necessarily on GCC. State chart is slow, but we didn't expect it to be fast since it generated so much code. SML, switch, if else, they're very well optimized because they're really easy to follow for the compiler to optimize. State pattern, well, if you care about performance, you don't really want to use virtual dispatch, right? Although it might be devirtualized sometimes, most likely it won't. You will have the heap and shared pointers and all that badness to deal with. So you don't want to do that if you care about the performance. Coroutines are quite decent. Probably they might be better, and it's just first stages of them being introduced. So maybe at some point we can actually improve them. Instructions per cycle. Well, the more instructions we can handle per cycle, the better. It just shows how good we actually utilize the CPU. If you have less instructions, we may not use. We may have not as good, results here. But it shows that all the solutions are more or less the same. Coroutines are a bit smaller than the other ones, but having a value around 2 is really good to have or keep in mind. Branches. So it's interesting how many branches actually MSM has because of the jump table. Besides that, inline versions have some more branches as well in comparison to all the others. But it doesn't mean that it will be slower because it's all about how many misses you got. And as you see, with the state pattern and virtual dispatch, well, we don't really hit it very well. Compilers are not really, CPUs are not really good in predicting where we are going. In other cases, it's much better. State chart, since it's using the virtual dispatch as well, it does have quite a few misses, but it's still not as bad as the state pattern. Compilation time, that's what I was referring to earlier. MSM compiles quite slowly in comparison to any other solution. So that's not good. If you really have to be productive, you can be productive with MSM by having declarative way of using it, but you pay for the compilation times a lot, really a lot. SML compiles quite fast. In the release, it's pretty much the same as MSM is just really slow to compile. And the size, because we care about the size as well. Size is really important for us to, if you care about performance, we probably care about the size. We have some restrictions on that. MSM produces quite a huge binaries in the debug mode because of the debug symbols. It's all, as I told you before, it's all MPL based. So we produce a lot of code in comparison to other solutions. But in executable, in the release mode, they are really small in comparison in MSM, in comparison to the debug mode. So that's really good, which means that everything is just thrown away. So yeah, we have like 10 seconds left. So the mission is to embrace zero-cost state machine libraries. And with that, we have actually zero seconds for questions. So thank you.